D.3, solve PDEs by Fourier transform. Yeah, so now Fourier series, Fourier transform. Another way, yeah, we can solve PDE. We take Fourier transform, just like Laplace transform, but this time we apply Fourier transform. All right, let's look at one example. Still one-dimensional heat equation, but this time we consider infinite bar. Yeah. So what's the difference? Infinite bar, yeah, no boundary, right? So both ends extended to infinity. So no boundary condition. Yeah. So we only have initial condition, yeah, but we don't have the boundary condition. Right? So for this case, we apply the Fourier transform. Fourier transform both sides of the PDE, left-hand side, yeah, right? Fourier transform second derivative. Yeah, so we have the formula, right? Second derivative. Yeah, we have the formula. Yeah. All right. That Fourier transform of partial derivative with respect to t. Yeah. So we can calculate it. Yeah. We apply the definition of the Fourier transform. Definition. Right. Partial derivative. Partial derivative, this place we did interchange, right? Yeah, so here. There is one interchange operation. Yeah. How can you move this partial derivative out of the integral, right? Yeah. Initially, it's inside the integral. Then we move it out of the integral. Yeah. So we did this step. Yeah. Remember, when the function is good enough, we can do that. Yeah. So there are some conditions, but usually we assume we have our function is good enough to support this interchange operation. Yeah. All right. Yeah. But there is some condition. Okay. Yeah. So you need to be aware of it. Yeah. If something is wrong, you need to check the condition. Okay. If everything looks all right, so then you can do it. All right. After that, then we have a new equation. Yeah? So this time, you can see the partial derivative with respect to t, only one variable. You can treat as ODE, right? Yeah. So this version, after you apply the Fourier transform, so you have a PDE. You have a simple first order ODE. First order ODE, yeah? So we can write a solution quickly, right? But when we write a solution, we treat W as constant. We do not treat it as variable, okay? We only treat the little t as the variable. Yeah. When we talk about ODE, so only little t is the variable. W, we treat it as a constant. So we can write condition, yeah, W, so there, because when we write a ODE solution, we need a constant in front of E, right? But that constant, our understanding is the constant should contain the W part. Yeah? Because we treat W as constant. Yeah. So the general constant expression should contain the W. Yeah? So that's why we have a capital C of W function. Yeah. Because later we need to treat the W as a variable later. Yeah. Yeah. So that's why we use that capital C. So we need to determine this capital C of W function. Yeah. That's easy because we have the initial condition, right? So we apply initial condition. We take Fourier transform on this initial condition to get a capital C function. All right. Apply Fourier transform So we treat x as the variable. Yeah. All right. So apply it. Yeah. Yeah. Because that's, you plug in t equals 0, right? T equals 0, so that's the capital C of W. Yeah. Okay. Yeah. So you plug in t equals 0, yeah. But this Fourier transform of little u when t equals 0, you apply Fourier transform on this initial condition. That's the Fourier transform of little f function. Yeah. So it's known. Yeah. Little f is known. So capital C is known. Okay. All right. Yeah. Now you need to calculate the inverse Fourier transform. The Fourier transform of the little u function is known. So to find the final solution, you just calculate the inverse Fourier transform. All right. Yeah. So you apply the inverse Fourier transform, the formula. Okay. All right. All right. Yes. There. Yeah. So you want to simplify a little more. Yeah. Although this is good enough, right? Good enough for your final solution. But there is one thing you want to make it more friendly. Yeah. Why? Although this final solution already is correct. Okay. Yeah, no problem. But the only thing is not that friendly is you have complex expression. Little I, complex expression. So the ideal case is you want to write your final solution as a real function expression, not a complex function expression. Yeah. Because our solution should be a real function, right? Yeah. Our solution should be a real function. Okay? Yeah. Yeah. So we want to see a real function expression, not a complex function. Although this complex function, when you do the calculation, your final result will be real. Okay? Yeah. The complex part will be gone. Yeah. Yeah. But here the expression is still complex. All right. So let's do some more work to make it a real function expression. Yeah. All right. So let's apply Euler's formula on this E function. Yeah. Also, we use the definition of the Fourier transform. Yeah? So this little E function, yeah, because this Fourier transform contains the complex components. Yeah. Yeah. So in these two places, you have complex content. Yeah. So you want to find a way to remove the complex part. Yeah. All right. Yeah, imaginary part, yeah, not complex or imaginary part. All right, yeah. So that let's replace the Fourier transform by this integral expression. So we have, double integral, but we, change the order slightly. Okay, yeah. So in this expression, you can see little f function, real function. Yeah, this first E function also real function. But the second E function is a complex function, little I there. Yeah. Second E function. Right? Yeah. All right. Yeah. Actually here, yeah. So I noticed a small problem here. Yeah. Here we apply two formulas. First formula, Fourier transform formula. This is a Fourier transform formula. Second formula, this one, inverse Fourier transform. Yeah. But for the Fourier transform, is there a negative sign here? We should have a negative sign here, right? Yeah, Fourier transform. Yeah. So here I took the screenshot from the textbook. Yeah. Yeah. So this probably, yeah, there is a typo here. Yeah, negative sign. Yeah. Yeah, because there, for inverse Fourier transform, we don't have the negative sign, right? Positive. Yeah, because the sign is different. For Fourier transform and inverse Fourier transform, the sign before that little I is different. One negative, one positive. You cannot have both positive, both negative, right? Yeah. So here, that negative. And also, that explains for this place, so you have the negative sign. Yeah. Otherwise, yeah. Otherwise, you have plus sign, right? You don't have the minus sign. You have plus. Yeah. Yeah. So that's why. Yeah. So I saw, how do we get a minus sign? Yeah. Because Fourier transform, it's negative. Yeah. Sign. All right. Yeah. Then, now, the only complex part is in this last E function, right? Yeah. Let's apply Euler's formula to separate, because we have real part and the imaginary part. Now we want to separate real part and the imaginary part. So we apply the Euler's formula. Yeah. So we have the real part, cosine function. Yeah. Imaginary part, this sine function. Okay. Then we take integral. Yeah. It's the first term integral, second term integral. Right. Yeah. So now we want to claim the integral of this imaginary part will be 0. Can you see that? The integral of that imaginary part will be 0. Can you see that? Yeah. All right. Let me show you why. Why the integral of the second part will be 0? Yeah. Because this integral is from negative infinity to infinity. Negative infinity to infinity. Okay? Yeah? The whole real axis. Symmetric, right? Positive half and the negative half. Now, let's look at the function of integrand, right? Integrand function. Okay? That's the integrand function. This integrand function, what is the variable? Let's look at the inner, this is the inner integral. In the inner integral, W is the variable, right? Yeah. W, dummy variable, right? Yeah. So dW, W is the variable, all right? So look at the integrand function. Is it an odd function? This integrand function is an odd function. Can you see that? So this function is sine is an odd function, right? Yeah. Sine function is an odd function. This E, because you have W squared, it's even, right? So this E function is even. Even function times an odd function, it's also odd function. Odd function, you take integral on the whole real axis, it must be 0. Okay? Odd, yeah. So you take integral on the symmetric interval, right? Yeah. On symmetric interval, cancel out. Positive half, negative half, cancel out. Okay? Yeah. So it's 0. So that tells us the imaginary part is gone. Yeah. It's gone. So we keep the real part, this cosine part. So we can write our final function, final solution in this real function expression. Yeah. So every function inside the integral is a real function. Yeah. No imaginary function. Okay? Yeah. Yeah. So then we feel more comfortable, right? Yeah. Yeah. So now you compare these two expressions. Yeah. So which one is more friendly for calculation? Right? Yeah. Yeah. Complex, real. Yeah. Because, yeah. Let me go another level. Yeah. Suppose, yeah, so now you have the expression for the final solution. Now I want to make some comments here at this point. First, if we compare the Fourier transform method and Laplace transform method. Yeah, so we can use the Laplace transform solve PDE, right? Yeah. So here we for PDE, solving PDE. Okay. So we have Laplace transform method and a Fourier transform method. Now, when we compare them, we can see Fourier transform method has big advantage, has some big advantage. Why is that? The reason is very simple. When we do inverse Laplace transform, we do not have explicit formula, right? Think about it. There is no explicit formula for inverse Laplace transform. But we have explicit formula for inverse Fourier transform, right? That's a big advantage. Yeah. So here you can see the final expression, we apply inverse Fourier transform. We have an explicit integral. We can write it out. Inverse Fourier, yeah? All right. But for some complex functions, if you want to write inverse Laplace transform, then we do not know how to find an integral expression. Yeah, that's a big disadvantage. Yeah. All right. Because the next step, since you have this integral expression, yeah, because eventually you need to calculate this function, right? Yeah. After you put solution, yeah. But after you have the solution, then in the real world applications, you need to apply this solution on your data, right? Yeah. You need to produce something. Yeah. This is the function, but you need to use this function to generate some useful data, right? Yeah. Yeah. So now you have this function. Yeah. So this expression, but this expression, it's hard to find an integral, right? Yeah. So for many complicated integral, even Wolfram alpha cannot do it. Yeah. There is a big limitation. Now, because this f could be arbitrary function. For some relatively bad function, right? or complicated function. Yeah. So we cannot say, complicated function. Yeah. It's very hard to write explicit, or people usually call analytic form of the formula, right? Yeah. So that's why people leave this big integral there, all right? Because nobody knows how to find the integral. Yeah. So even you apply powerful software, it's also hard. Okay. Yeah. In that situation, yeah. In the real world applications, if we have this formula, we can calculate the integral using numerical methods, right? Yeah. Numerical methods. Think about that. Yeah. Because in the application, you need to use these functions. Yeah. We have numerical calculation. Yeah, we know how to calculate integral numerically, right? Yeah. Simpson method. Yeah. Yeah. All right. Yeah. There. Yeah. But here, think about. So here, I just want to do a little more discussion. Yeah. So suppose you have this function as your solution. Yeah. So it is a function of two variables, x variable and t variable. Yeah. How do you produce the data for this function? That's the question. No. So you have the expression, but when you need to use this big expression, it's hard to use, right? That big expression. Big expression. How to work on, right? How to do the work. Yeah. All right, so here we go the numerical way. Yeah, numerical way. Okay, all right. Suppose we consider, domain, domain of the function. Okay, so we'll consider domain of the function. Okay, so here I use this square or rectangle represent the domain of the function. Can we draw grids? Draw grids. Grid. Okay. X and T, or Tx, okay. 2D, okay, grid. So T-axis and X-axis. So we have data points, the points on grids, right? Or evaluation point on grids, okay? Yeah, so these grids, okay, let's say xj, tj, okay? Each point in the grid, we have x coordinate, t coordinate, yeah. So then, when you take the x, so here, xj, tj, there, yeah, so the constant. All right. Can you find the numerical value for the integral? This double integral, this time you have double integral. Okay? Yeah? Yeah. So if you can find that, you have one data point. Okay? Can you find the value for all your data points on the domain? Generate. Yeah? So your data points, it's a grid. It's like a net. Okay? Yeah? Or mesh. Yeah? Okay? Net. Okay? Yeah. So that's the data you use to describe your function. So here you use the discrete. That's the discrete representation of your function. Yeah? Your function is a continuous function, but your function is too complicated. So now you have some discrete way to represent your function. How about that? Yeah. Then this discrete data you can apply to solve your real world problems. Yeah. If you need to use this function, yeah, because you have the data generated from this complicated function. Okay? Yeah. At least you can do the work, right? You can do the work. Okay? When you have an expression, you can do the work. Okay? If you do not have the expression, then you can do nothing. You can do nothing, right? Yeah. So now you can generate the data needed. All right? Yeah. So here, that's just my comment. Okay. Yeah. Because we need to think about the real world applications, right? Yeah. Not just the formula. Okay. We put there formula. Yeah. How to apply these formulas. Yeah. We need to think about those things also. Yeah. All right. Then last topic, numerical solutions. I just talk about the general ideas. Yeah. The general idea is very simple, but very useful. Yeah. So here you can see in our real-world applications, most of the time we need to work on the numerical calculation. Yeah. Numerical calculations. Yeah. All right. Yeah. So there, solving PDE numerically. Yeah. Let's look at the simple, basic idea. Use difference equations. Yeah. So PDE, partial differential equation, partial derivatives, too complicated. So now we want to replace it. Replace partial derivatives by difference expression. Difference expression. Yeah? So let's see how to do it. We use the approximation way. Yeah. numerical solution always approximate solution. So here we do not expect to get exact solution. We just want to get good approximation solution. All right? Yeah. All right. Approximation. How to do the approximation? Replace the partial derivatives by difference quotients. Difference quotients. You take the difference first, then you need to take a quotient. Yeah. So difference quotients to replace partial derivatives. Okay? Yeah. How to do it? Yeah. So we base on the Taylor formula. Yeah. Taylor formula can tell us that's the good approximation way. Okay? So let's look at the Taylor formula in two cases. Yeah. The first one, x plus h. Yeah. This h usually a small number. Yeah. X plus little h. The second one, x minus little h. So we write their Taylor expansion out. Yeah. Yeah. So two variables, x variable, y variable. When we do the Taylor expansion on x variable, we treat y as the constant part. Yeah. So we only treat it as one variable. Yeah. Okay? Yeah. All right. So we have the there. Now let's look at the first derivative. Yeah. First derivative expression. Yeah. You can see the first derivative approximately equal to the difference. Yeah. Difference of these two. So cancel out. Yeah. Think about it. When we take the difference, this term cancel out, right? The first one. The square term also cancel out. Okay? Yeah. They're high order terms. Now for this term, 2h times u partial x. Okay? Yeah. So that's why we divided by 1 over 2h. Yeah. So the difference. Yeah. The difference of these two function values, we can approximate the first partial derivative. How about that? Yeah. We know there is some remainder part we omit. Yeah. So we do not include the remainder part. Yeah. But that remainder part, because it has the order h cube order, right? Yeah. So yeah, because when we calculate approximation, we take a very small h. Yeah. H number is small. Then h cube much smaller, right? Yeah. So here 1 over 2h. So you still have a square, h square term, right? Yeah. So very small. So the error part is when h small, the error term very, very small. Okay. So that's why we have a pretty good approximation. Yeah. This is a good approximation. First derivative. Similarly, we want to calculate approximation for partial y derivative, right? First partial derivative with respect to y. So this time we apply Taylor formula on variable y. So plus k minus k, right? Yeah. So cancellation. Yeah. So we have the partial u partial y first partial derivative in that expression. Okay? Yeah. Next, we need to do second partial derivatives. Yeah. All right. So this time, still, we apply the same, but the partial, yeah, this time, think about we add up these two, right? We add up these two, there, the other terms are canceled, right? Yeah. So we add up these two. The other terms cancel out, right? This time. The other terms cancel out, right? Yeah. So we only keep the even terms. Yeah. Even terms, 2 times u, 2 times u, and h squared, 1/2, 1/2. So h squared, right? Yeah. So from this one, we can approximate double partial derivative in this expression. Okay? Yeah. Approximation also very good. See? Yeah? The approximation, very good. All right. Then, similarly, yeah, double partial derivative with respect to y. Yeah, yeah. So here we do the difference quotient on y variable. On y variable, right? Yeah. But sometimes we need to do the mixed second partial derivative, mixed. Yeah, partial y, partial x, partial y. So the first time, yeah, so we do twice. The first time we do partial x. The second time we do partial y, right? Yeah. So after we do twice, so we get a mixed partial derivative. Yeah. Approximation, all approximation. Okay. After we get all these approximations, then we can replace all the partial derivatives in the original equation, PDE, yeah, by these, people also call divided difference. Yeah, divided difference. Yeah. Difference, then you do division, right? Yeah, division. Okay. Yeah. All right. All difference quotients. Yeah. All right. Difference equations for two PDEs. First one, Poisson equation. Second, Laplace equation. All right. The Poisson equation, yeah. There, yeah. That's the. Yeah. So what's the Poisson equation? Yeah. So very easy. Yeah. Double x plus equals f of it, fxy. Okay? Yeah? Then, yeah, we just apply the, approximation expression. Yeah? These two partial derivatives. Yeah? So h squared. Yeah, that. Yeah? After that, you can see, yeah, we do not need to work on any partial derivatives. Okay? We only work on the function values, right? Yeah? So easy. Only work on the function values. Yeah. Laplace equation, we just change this Poisson equation, make little f to be 0. Yeah. F function becomes 0 function. That's the Laplace equation. Then, so the x, little f 0, so the right hand side 0. Yeah. So that's the equation. Yeah. But how to solve? I will use the heat equation example to show you how to solve, how to find a solution. All right. H, we call it mesh size. When H, yeah, because the mesh size, yeah, to have good approximation, we want to make H very small, goes to 0, yeah, because people want to study the convergence. If the solution you find in this approximation way can converge to the final real solution. Yeah? So people need to show where h goes to 0, your numerical solution needs to converge to the real solution. That's the convergence question. Yeah. Yeah. Yeah, so that's an important problem to study. Yeah. All right. Another way to represent, yeah, because for the equation like that, sometimes it's relatively hard to memorize. So people use the, direction, east, north, west, south. Okay. Yeah. So use this, diagram to show. Yeah. The current point at x, y. So the east point. Yeah. So x plus h, right? X plus h, east point. North, yeah, y plus h, right? Yeah, north, y plus, things like that. Yeah. 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 So the way just help you to memorize the pattern. Yeah. Then coefficient scheme or stencil. Yeah. Some people also write, try to write the formula in some special pattern. So this is, the stencil, yeah, people use to to represent the coefficients. Yeah, coefficients. Yeah, yeah. All right. Yeah. Yeah. Then, the last thing I want to show you, one-dimensional heat equation numerical solution. I want to show you the details. Yeah, use this simplest example to show you how people use the numerical methods to solve PDEs. Yeah. So from this simple example, you can get a good understanding. Yeah. All right. First, let's look at the equation. Yeah. So we're familiar with this heat equation. All right. Then let's use the difference equation to represent the original PDE. Yeah. All right. Yeah. First derivative. Yeah. We have the first derivative. Okay. Yeah. With respect, yeah, partial derivative with respect to t. So we use second subscript j plus 1. Yeah. That corresponds to the t variable. Okay. The difference quotient corresponding to t variable, right? Yeah. For x variable, yeah. So our first subscript, I subscript, corresponds to the x variable, but we need to use the second derivative representation. Yeah. So that's the, our approximation equation, difference equation. Okay. All right. So we write it in another way, yeah, because this k we call the step size k, yeah. In the t direction, we use step size k. X direction, we use the step size h. Yeah. But we want to put them together. These two step size, put them together. We use this little r to represent k over h squared. Then we have a version, we only need to use the parameter r, little r. Okay? Yeah? So we have the simplified equation using little r. All right. Yeah. Then, yeah, people study that little r related to the convergence question. Now, if the solution calculated in this way would converge to the real solution. That question. Okay? All right. So condition for convergence. The condition is very simple. If this little r is less than or equal to 1/2, then it is guaranteed the solution is convergent. Yeah, that's good. Yeah, that's pretty good. Yeah, people can control easily. Yeah. So 1/2. 1/2. Yeah. All right. Then the stencil. Yeah. Because you look at that. The stencil. Uij, that's this point, right? Uij, okay? Ij plus 1. So Ij plus 1, that's that point, okay? All right. Yeah. I plus 1j, this point, okay? All right. I minus 1j, that's this point, yeah? Okay, yeah. So you apply this stencil to, to give you the relationship, this time among these 4 u values. Okay, the location. Yeah, you also look at the, other than the values, you also look at the locations of these 4 values. Yeah, like in this shape. Okay, this shape. All right. Now with that preparation, now we are ready to the last round numerical calculation. Okay, last round numerical calculation. Our goal, we want to find little u for the little u value for all sub I and j, right? Yeah. If you can find all the values, yeah, it's on the grid, right? Yeah, because you arrange all this little u, the values, on the grid, right? In the domain. Yeah. All right. So here, let's draw that domain. This is the domain, okay? Yeah. T-axis, x-axis, okay? The boundary condition. U equals 0 in this boundary. U equals 0 in this capital L equals 1, okay? So 1, boundary. And the initial condition when t equals 0, your u equals little f function. Yeah. So the value on this edge, okay, this edge, it's known, okay? All right. So when we start, we need to have initial values, initial known values. Right? So what are initial known values? All these values known, right? Initially known values. All these values initially known. Okay? All right. And before we do calculation, all these little circle points unknown, right? The values are unknown. All right. Okay. Now we do calculation. When we do calculation, we apply this stencil on these 4 points. In these 4 points, 3 known values, 1 unknown. Can we find the only unknown value? Yeah. So after we apply the stencil first time, that this point known becomes known, right? All right. Then another run. Can we apply that stencil on this local area? That this value is known, right? Then we do things like that. No. Then after that, no. So row by row, we can find all the values, on the grid. Yeah, that's the solution. Yeah, that's the solution. Okay, numerical solution. Yeah. So you can see the method is very simple. You do iterations. Okay, you do iterations. So the boundary values can be used. Yeah, follow some order, certain order. Yeah, you write a computer program, right? Yeah, so you program. But if you want to get a good approximation, you want to make the little h very small. Little h very small. Yeah. So your approximation will be very good. Yeah. All right. Yeah. So that's everything for this semester. Yeah. So and lot of part, yeah, because I cannot give you the computation question. So a lot of part you may see in the last 2 quizzes, quiz 5, quiz 6. Yeah. But I give you some basic questions, yeah. Not the deep questions. Yeah.
This part?
Yeah. Yeah, all these part, because we have no chance to put it in the computation questions. But you will see in the concept questions. Yeah. All right. Yeah. Yeah, just some general basic questions. Yeah. All right. That's it.